So stability is nuanced and multi-layered when you consider it from a nonlinear standpoint. In a linear system, stability is pretty straightforward. If you slightly disturb the system, it returns to equilibrium in a sort of a predictable manner, speaking mathematically. But that just doesn't happen in nonlinear systems, or at least it generally doesn't happen in nonlinear systems. They have strange behaviors. They have multiple equilibria, sensitive dependencies, and sometimes they don't even return to equilibrium at all. Like that's also possible. So I think this is the reason, the primary reason why we have several precise definitions of stability instead of just having one universal definition when it comes to nonlinear systems. I think there are like six or maybe seven most commonly used definitions for stability. The most common that is often mentioned in most of the physics and math textbooks that deal with nonlinear systems is what's called the Lyapunov stability. So Lyapunov stability, you can think of it in terms of by taking an example like a satellite in an orbit or something, because if you consider a satellite, if its trajectory stays within a certain bounded region without escaping or spiraling out of control, then it's essentially considered stable. That's basically what Lyapunov stability is. You can think of it in terms of like if I start close to equilibrium, do I continue to stay close to the equilibrium? That's basically the idea. So a satellite in orbit is like a classic example of what we call Lyapunov stability. There's also asymptotic stability, which is basically it's like a stronger condition where it says that not only does the system stay near equilibrium, but over time it actually moves back to it. Let's say like a pendulum, for example, is a good example. Like if you push it and it oscillates, eventually, thanks to damping, it will eventually always settle back to the lowest energy state. So that's asymptotic stability. We also have exponential stability. That's another commonly used definition because we see it happen every single day. Like for example, temperature dissipation. A hot object in a cold room doesn't just cool down; it cools down exponentially fast at first, then slows as it approaches room temperature. So this is a commonly used definition of stability in say control theory, for example, because we prefer exponential stability over asymptotic stability because we want systems to recover predictably and quickly in control theory. So yeah, that's exponential stability. And then I think we also have BIBO stability, what's known as BIBO stability. That BIBO is an acronym for bounded input, bounded output stability. This basically asks, if we keep the inputs to a system within a certain range, do the outputs also stay bounded? Like that's the question that BIBO stability asks. So you can think of it in terms of like say an audio amplifier, right? If you feed it a small bounded signal, you don't want it suddenly blasting at full volume, right? If a system is BIBO stable, bounded inputs always result in bounded outputs. But if it isn't tiny changes in input, it can cause runaway effects, like for example, let's say finances, right? In finances, small economic shocks can lead to catastrophic collapses. So, bounded inputs, bounded outputs. This is another stability. This is another definition of stability that is, considered in nonlinear systems. And then we also have structural stability. So, in structural stability, the question that we ask is, if we make slight tweaks to the system overall, does the system still behave the same way? And if it does behave the same way, then we call it structurally stable. Like a good example is an airplane. So imagine an airplane in turbulent conditions. When the weather is inclement, the structure of its control system still functions. Like, even when minor environmental changes occur, like wind shifts, turbulent conditions, small mechanical deformations, the plane still manages to stay in the air, so it is technically structurally stable. And we also see this happen a lot in biology, like, for example, our heart rhythms stays pretty stable even when there are small changes occurring. You know, a heart should keep beating stably, even if there are small variations in neural or electrical signals. Otherwise, things go very wrong very quickly. And yeah, so these are generally the definitions that are commonly used in nonlinear systems. There's also some systems, particularly chaotic ones, that exhibit behavior that is sensitive to like initial conditions. I think you may have heard of the term the butterfly effect. So this is the sort of an example of a butterfly effect, which it means that when a system starts at near equilibrium, a small perturbation can cause completely unpredictable outcomes. This is also seen in weather systems, for instance. Like, they follow nonlinear equations that are highly sensitive to initial conditions. That's why we can predict the weather for a few days, but long-term forecasting is inherently unstable and generally wrong. So yeah, this is, I think these are the reasons why stability is not really a single concept.